So I'm going to talk about the adaptive multiple importance sampling that we've built into SmartDT now. So let's start off with the motivation. If you look at Monte Carlo sampling, so a standard Monte Carlo sampling, you would have just sort of a plotted on the standard normal space sort of plot. You just have these sort of circles, concentric rings, where you'd be generating samples. Inside the innermost ring, you'd have 99 out of 100 samples inside of there. As you go out, these are orders of magnitude of samples to get samples outside of each of the rings. By the time you get out to this brown ring, and these are just default colors, but you have only 1 in 10 to the 7th samples is going to fall anywhere outside of that outermost ring. Now, consider also on this that your failure region that you are concerned about evaluating what's the probability of getting a sample in this failure region is only going to be on one side or so of this graph. So now the probability of finding samples inside of the failure region is even smaller. So when we talk about how many samples you would need to do a Monte Carlo analysis and get a converged result, there's kind of a simple equation you can use to calculate that. The number of samples you would need is 1 minus the probability you're computing divided by that probability times the coefficient of variation squared. So if you take that and you plug in a probability of 10 to the minus 7th and the coefficient of variation of 10%, that will give you the 10 to the 9th samples that we've put up in some of our slides. So going on further towards what is important sampling, just take this example. The optimal region to put samples to estimate the probability of failure would be here in the red, given the failure region drawn on the previous graph, and where your PDF function is largest, so close to the origin. So if you looked at the probability of failure and looked at how much of that probability of failure from that entire region on the previous graph was inside of just this part, that's 99% of the POF. So if you can accurately sample that region, you can estimate the POF with coefficient of variation of 1%. So let me introduce the basic importance sampling. So standard Monte Carlo sampling, you're trying to estimate probability of failure, probability that a sample falls into this region. And you're generating samples from this joint probability density function that's just concentric rings at the origin. So that's what we've been talking about. 1 10 to the 7th is going to come outside far enough to get into there. And then you've got limited space or limited angular region where they'll fall into the failure region. So most of the samples you generate outside of the 10 to the 7th ring are going to not give you any information. With importance sampling, you can choose where to put your samples. So you construct a sampling density and you sample there. And if you know where to sample, you can very quickly estimate the probability of the failure region. The problem with importance sampling is knowing where to put the samples. So here, just for reference, are the calculations that are involved with Monte Carlo sampling. This expectation function with Monte Carlo reduces to calculate the mean to a simple summation of the number of samples, this is your 1 minus FEVD. So whatever the expected value of this function is, you just sum that function over the number of samples and divide by the number of samples. To get the variance, you can do it this way. It's harder to calculate a variance than it is a mean. So if your mean is you're not getting enough samples to accurately predict the mean, you will probably not also get a very good estimate of variance. With importance sampling, all you're doing is taking this and you're plugging in a new probability density function that you're going to sample from. But now you have to correct for the fact that you're using a different sampling density than the nominal density that describes how your variables are distributed. So you add or include an importance weight, which is just the ratio of the nominal density to the sampling density. And if you look here, if you can see that those just cancel out. You'd be left with the same equation over here. When you go to sampling, then there's nothing in here to cancel out anymore. So you include the importance weights in your sampling to correct for the bias that sampling from a different distribution than the variable's nominal distribution would introduce. And then you can also compute a variance, which is how we compute coefficient of variation, which we'll talk about in a moment. So having introduced the concept of importance sampling, now we can look at what is involved with applying importance sampling to probabilistic damage tolerance analysis. And the problem is not that importance sampling is inefficient, it's just that for different time points in probabilistic damage or calculating the POF, the important region of the variables is going to shift. So if you adapt a sampling density for the middle distribution, say 10,000, that's going to give you a very good estimate of the POF curve here, but you will not get a very good estimate here or here. So with traditional importance sampling, you have to adapt multiple sampling densities, and the adaptation process requires sampling, iterative sampling. So if you have several time points and you have to perform multiple iterations of optimization at each POF time point, it can become cumbersome and inefficient. So again, illustrating that point here, this adapted sampling region for basic importance sampling would only give you a good estimate for the POF here. These are ideal important regions, or if you knew perfectly after the fact or before the fact where to sample, you'd sample these, but you don't. So these were calculated after the fact. And then you would have to adapt multiple sampling densities in a repeater loop to estimate all of these. With adaptive multiple importance sampling, what we're doing is we're adding sampling densities one at a time to approximate a density that you could use for any time between 0 to 20,000, let's say. You give it a time range. And after you've added a sufficient number of densities, you have something that looks similar to the ideal sampling density. And you can use that to evaluate the POF at any time point in this range. So instead of adapting an individual sampling density, you're adapting a mixture of sampling densities to approximate an overall range of POF times. This slide is just included for reference. It's how you go from individual sampling densities to a mixture density. So the importance weight that we talked about on the first importance sampling slide is here. It's just a weighted sum of some mixture weight times these individual sampling density importance weights. And that's really all I wanted to say about it. It's just, when you talk about a mixture sampling density, this is how you do it. And it turns out that there are multiple ways to assign mixture weights. The one that we're using was developed by some guys at Stanford. They were computer science, ray tracing graduate students studying ray tracing, and their work ended up being used to speed up the rendering process for studios. They actually, the inventors of the method, or these sampling weights, won an Academy Award for the the fact that that was used on the Avatar movie. So once we have a mixture that we're going to adapt, the next step is, well, how do we adapt that mixture to estimate the probability of failure? So what we're doing is we calculate at each step, we calculate the PLF curve. We find the point where the coefficient of variation is highest. So we're estimating both PLF and its variance, calculating coefficient of variation, find where it's highest. Then we add a sampling density that's targeted to reduce the PLF coefficient of variation at that point. And what you can see is by doing that, you don't affect just one time point, you affect several time points around it. So all of these values got reduced. And so at the next step, you again calculate the entire PLF curve. You look at all the coefficients of variation, and you find the next maximum coefficient of variation point and add a sampling density targeted to reduce the variation there. And you repeat that process until all of your PLF estimates have coefficient of variation that meets the threshold. So just driving the point home. So this is the progression of mixture densities from an initial, after initialization point, progressing through adding one at a time until you get to the point where all of the PLF estimates meet the threshold, and it's approximating this ideal density shown here, bottom right. So all I'm going to do is show an example now. This is the form for entering or to go into adaptive importance sampling, select adaptive importance sampling in SmartDT. It's on the analysis pane, and you select probabilistic on the side menu. Where you have seen Monte Carlo sampling before, you would select adaptive importance sampling, and then you can enter a random seed. That's because we're using sampling. That's used to initialize the random number generator for all of the samples. You enter your threshold coefficient of variation, the number of samples that you generate for every mixture density or component density that you add to the mixture, and a maximum number of iterations. So if you reach this maximum number of iterations and the target coefficient of variation is not satisfied, it'll stop there and give you the estimate that it had. Because we're assuming that as we move on and include NASGRO or other crack growth software, that somebody might want to stop and change something if the analysis is not converging. That hasn't been much of a problem with what we've done so far. So I have an example problem. It's very similar to the one that Juan showed. It's the corner crack growing from a hole in a wing spar. But this time, since we're using adaptive multiple importance sampling, we can generate a crack growth curve for every sample instead of using a master curve. And that allows us to vary the DADN and the aspect ratio, and even add the hole diameter just to the random variables. So that file is in your user folder or training materials. You go into the adaptive sampling subdirectory AMIS example. Sorry, don't double click on that. And load the SMDT file in SmartDT. So you can see adaptive sampling is selected. The default is left at 0.2, but I often use 0.1. Sometimes 0.2 can give you a little bit of a rough PLF curve, but it's still rough about the average accurate value. We're using the 7475 aluminum material from the database, but this time I've added some DADN variability or random variable definitions. So I've got the Paris coefficient with variation, the Paris exponent with variation, and a correlation coefficient for those two variables. Geometry is the same as what Juan showed, except now I'm adding a normally distributed aspect ratio that has a mean of 1.5 and 0.1 standard deviation. I think Juan, you didn't cover this one because hypergrow requires a constant amplitude loading spectrum definition. That's to grow the crack. It's not the same as the extreme values that you would encounter in the flight, because that's only once per flight. We're talking about, with the constant amplitude spectrum, we're talking about cycles that would occur multiple times per flight to grow the crack. But it is constant amplitude for hypergrow. So here we have a cyclical stress of 5.5 KSI 55 times per flight. No inspections. So how am I doing on time? Do I have a few minutes? So I can give you an example to show the speed up. If I just do 1 million samples with Monte Carlo, start the analysis. It's using a lot of parallel processing, and Monte Carlo is embarrassingly parallel, so you get good speed up with it, but still 12.6 seconds. And when I look at the results, you can see that somewhere in here, the Monte Carlo results don't converge anymore. You didn't generate any samples that failed, so it drops to 0. When I go and select adaptive sampling, the run finishes in under 0.2 seconds. And now the results are converged all the way down to this 10 to the minus 18th. So this here would have required in Monte Carlo probably 10 to the 20th samples. So, where's that example? Okay, I opened it from the adaptive sampling folder AMIS example file.